presentation of these structures. And now we want to see, what if I have double bonds? In the case of single bonds, as I showed, most of these sticks are single, basically, which shows having a single bond. When we go to the double bond, we will show that with two sticks, okay, like this. This is the structure of ethane, okay, the second hydrocarbon components, which has two carbons, okay, sorry, ethene, which has two carbons, but since it has a double bond, it's called ethene, okay, and this structure is more reactive than the same structure like ethane without having a double bond. Okay, we'll go over their nomenclature as well. Okay, so generally, if we want to show the structures, we show them, and then we show the elements, and then we show their bondings, like carbon dioxide, okay, or CO2. Carbon has four bonding, oxygen has two, so this has been the structure of the carbon dioxide, which carbon and oxygen are sharing two electrons, okay, or hydrogen cyanide, which nitrogen is sharing three electrons with carbon, and carbon shares one with hydrogen, or methane, which are all single bonds. So this is a single bond, this is a triple bonds, and this is the double bond, okay, structures. They can also get more, complicated with the hydrocarbon components start making bondings with oxygen, you know, as a branch or inside the structure. Okay, so these are different form of these structures that we'll go over very shortly on their nomenclatures, how to name them, how to show them. Okay. Sometimes people they don't show the bondings; they just show the structure without show the names without and the structures without having the bonding. But this is not the practice that we wanted to do in this class. In this class, what we want to do is to show the bondings. But for hydrogen, you are free to show it or not show it. Okay, because hydrogen we know hydrogen has one bonding. Okay, so there is no need to show that. But for the rest of it, we need to show them because it's much easier to recognize which structure is a single bond, double bond, and a triple bond. And as we said before, we are going to divide these structures in different homologous series, and these homologous series are based on the similarity in the structures. So what we are going to do, we are going to put all the single bonds in the one structure, double bonds in the other structure, and then triple bonds, and then cyclic structures. So we are going to separate them based on their bonding. So it's very helpful to see the bondings when we are drawing their structures. Okay. Okay. As I said earlier, one of the reasons that we are going over this organic chemistry again is the new applications of these structures and the organic chemistry in oil and gas industry. This is one of the very good examples of the application of these structures in the oil and gas industry. Oil and gas industry. This work has been completed with my former friend Mary Diaz when she was a master's student at Oklahoma University. She was a chemist by training, and she joined our program and she completed her master's in application of the organic chemistry and the link of that with the oil and gas industry using the what we call molecular dynamics study. And this is one of the pioneer studies in the application of the molecular dynamic in oil and gas industry. Um, so what she did, actually she graduated and then she joined Schlumberger, but unfortunately we lost her 3 years ago in an accident. But she was one of those bright minds that contributed to our industry. So what she did in this study, basically, as you can see here, it says bulk. When we are talking about bulk, we are talking about having the fluid in a bulk system, like having it in a very conventional macroscopic scale system. Okay, which what do I mean by that is when the system doesn't affected by the container. Like if I'm studying, let's say, hydrocarbon fluid properties, I'm looking at the pressure of that fluid, temperature of that fluid, volume of that fluid. I don't care if that fluid is in the cylinder made of plastic or it's in the cylinder made of iron. Okay, I don't care. I just care about the pressure of that fluid, temperature of that fluid, and volume of that fluid. Okay. However, so that's bulk. However, in the unconventional reservoirs that I am sure you have heard about, that like the shales, production, gas production, and oil production from the shales, we are talking about a pore size systems which are very small, okay, in the order of nanometers, okay, 10 to the power minus 9, okay. So these very small pores are such that they're impacting the properties of the fluid, okay. So the fluid property is not just affected by pressure, temperature, and volume of the fluid. It's also affected by the container where that fluid is located. If the same pressure, if the same fluid with the same volume and pressure and temperature is sitting in a bulk system or is sitting in a 1 nanometer tube, the behavior would be completely different. Why? Because the molecules of the container start reacting with these. Okay. It doesn't mean that when you have a large container, you don't have that reaction. You still have a reaction, but in that bulk container, in that big container, you have so many molecules of the fluid inside, in the system, and the interaction with the molecules with the container is very limited. Only few number of those molecules are in contact with the container. But when you shrink that container to the very small cube, you are increasing the area, the surface area that this container is intact with the fluid. So there are more interaction, and then as the interaction between these fluid molecules and the container, in compared to the interaction between the fluid molecules goes up, then you will see the effect on the fluid behavior. So what she did here, she basically is looking at the methane dissolution in water. She wants to see how methane will dissolve in water. Okay. So how much gas I can dissolve in water. It's like carbonated water, like you are drinking Coke, How much of gas can be dissolved in that glass of water, or glass of Coke. Okay. So it says, if I'm looking at the bulk, if the system is such that the container doesn't impact the behavior of the fluid, that amount is 1.6 standard cubic feet of methane per barrel of water. Okay. So it's what we know. It's a conventional studies. However, if you shrink the size of that container to 20.8 angstrom, which is 2.08 nanometer, then the amount that we can dissolve becomes more than double. So it becomes 3.8 standard cubic feet of methane per barrel of water. So it's the same methane, it's the same water. What we did, we just simply shrink the size of the barrel, the size of the container. We have one barrel, but instead of having it in a big barrel, we are going to have it in a very narrow, nanotube. And then she said, if you drop even the size to 1.6 nanometer from 2 nanometer, then the amount will go up to 8.4. And if you continue doing that and you go to the 0.69 nanometer, the amount is 22.2. So standard cubic feet. So from 1.6 to 22.2, so like 20 times more gas can be dissolved in water if you simply shrink the size of the container and make it nano tube. Okay, it has a huge application, and one of them could be in the gas storage. You want to store gas. How much gas you can store in a glass of water versus the same versus the amount of gas that you can store in the same volume of glass of water, but made of all nanotube. Okay, if you think conventionally, you might say, okay, in the empty glass, I have more free space, so I can put more, dissolve more gas. But in a same glass with made of all these nanotubes, like those nanotubes, these are tubes, like they can take spaces, so you have less space, so you should be able to store less gas. But now, when you have these nanotubes, they start interacting with the gas molecules. They're impacting the gas density. You will have a denser gas, stored in those nanotubes. Therefore, the amount will go up. So this is one application, very modern. Has a lots of application in different industries. And the other application is on simply measuring the properties of these shale reservoirs. So if you have bulk, if you have the conventional reservoirs like sandstones or carbonates, these are made of big pores, okay, in the order of micrometers, or in the order of millimeters even, okay. So these are big pores. And what's the size of the gas molecules? Like methane is 3.7 nanometer, okay, 37 angstrom. So 3.7 nanometer is the size of the one methane molecule, okay? So this is very small in compared to the millimeter or micrometer pores, okay? However, if you have pores which are like 1 nanometer, okay? So sorry, the methane is 0.3 nanometer, 0.37 nanometer. So if you have a pore which is like 1 nanometer, okay, or 5 nanometer, which like Marcellus Shale has a pore size, the average pore size diameter of 5 nanometer. If it's like 5 and then you have like 3.7, let's say 4.4 nanometer of carbon, methane, then you can only put 10 of these molecules in one cross section of the pore, okay? So 10 molecules will fill the cross section. So 2 of these molecules will be in contact with the wall, so 20% gone. And then you will have like 3 in the middle. So and you have to define this behavior of the 3 molecules in this case, which is like very hard. You don't even have a phase with 3 molecules to define its properties. So when we measure the porosity, which is one of the major properties of the rock, and we use that to come up with the original gas in place and how much gas we have in the reservoir, we usually use helium, okay, in our industry. But helium is much smaller molecule in compared to the methane. So if you have multiple pore sizes, that helium can access the large pores, intermediate pores, and very, very small pores. However, since you have methane in your reservoir, and if the small pores are in the order of nanometers, then these methane molecules might not be able to access all those pores. So they might just only be able to access these pores, or even just these pores, okay? So the structure is different, and then if you don't have access, then you cannot measure those pores, okay? Or if you use helium, you measure very, very small pores which are not available for methane, you are going to overestimate your gas in place. Or if you have a structure like CO2 like this, which is more of a planar structure, this planar structure can get into the small pores, while the structure like pyramids, they cannot. So the structure of these molecules impacts the physical property that we measure, like porosity. And if you don't have a good measurement, then you're going to have misunderstanding of the porosity estimation. And then if you do estimate the porosity, then you're going to have completely different original gas in place. So, and then you're going to, hurt your company. So it's very important to know. And when we know these, if I'm sending the sample out, the shale sample, I can ask the laboratory, hey, if you are going to measure the porosity, you better use methane to do that. And if you are using other gases, then you have to do the correction. So you are not just sending the sample out and receiving the results and using it without knowing what's going on, what they have used and how they have used it. So these are very important information, and that's why we're going to study these. And we can discuss these in more details, but this is, I think, is enough for now. Okay. So we'll continue to the next part of the lecture.